Yes. Meine Damen und Herren, Mesdames et Messieurs, ladies and gentlemen, willkommen, bienvenue, welcome to the positively last talk of DjangoCon Circus. If you don't count the lightning talks, and you should count them because they're really nice. So my name is Lennart. I work a little bit with Django, and I work a little bit more with Plone, actually. And as a comment on that is that the next version of Plone is going to have dynamic models by default. And in fact, the Nuxeo CPS, which me and Tarek worked on years ago, had it in 2004. If you're using a good database, i.e. not SQL, it's easy. But this is going to be about old code patterns, both real and mythical code patterns. And I'll start off with a pattern about dictionaries. And this one is a fairly common pattern. When you have a lot of values per key, so that every value in your dictionary needs to be some sort of collection, a list, tuple, dictionary, or anything mutable, in fact, you typically use a default dict, right? And the default dict essentially means that if you access a key that doesn't exist, it will create the key. So we create a default dict and say that the default value for any key should be a set. And that means we can assume and rely on that the key exists and that it's a set. Because if it doesn't exist, it will be created. But this only landed in Python 2.5, so what did you do before that? Well, it's very easy. You did your check manually. So this simply checks that if this key is in the data, in the dictionary, then it adds the value to the set that should be there. Otherwise, it creates the set and sets it. Now, the question is then, why do you need to know and recognize this pattern? It's outdated. You won't use it. It only exists in old and unmaintained code, right? And I find this example here. And why is this old pattern in Django 1.5.1? Well, because the code once supported Python 2.4. It doesn't support that anymore, but nobody's changed it because it works. And you don't mess with code that works. So when you need to, you don't need to, but it's good to know about some of these old patterns when you encounter them, even if you wouldn't use them, because once you dig down in any sort of code that is in a framework that has existed for a while, you'll encounter these kind of patterns. And then you just go, why are they doing this? And this is why. Because once default dict didn't exist. And you might think, because I thought, maybe the clever core developers actually are doing this for a reason. Maybe default dict is slow. So I checked, and unless the core developers are using Python, it's faster. So on Python, for some reason, default dict is actually very slow. Using default dict means also that there's less code, so there's less bugs. So that's good, and it's faster. Enough about dictionaries. Now sets. Sets are very useful. The values in a set must be unique, and lookup in sets is fast. So if you check if a value exists in a set, that's much faster than checking if it exists in a list. Although they aren't ordered, which is just both good and bad. And sets first appeared as a standard library module in Python 2.4, and is a built-in type in 2.4. So what did you do before? Well, what else do we have that has unique values, fast lookup, and no ordering? Yes, I lied. It's about dictionaries again. So before sets, you would use dictionaries. And I can't find any examples of this in Django, to my disappointment, and this is probably because Django's first supported Python version is 2.3, I think. I don't know, I didn't use Django then, but as far as I could figure out, it supported Python 2.3 from the start. So it's already always have had sets. But this code here will simply take a list of things and put the values as keys in a dictionary with none as a value, and then pick out the keys again. And this is not an uncommon pattern you might encounter to make a list unique. Today you would of course just make a set out of it instead. And also sometimes you would find that values are stuck into a dictionary as keys because the lookup was faster. So to check if a value existed in a dictionary is much faster than in a list. It's in fact around this much faster if you have a huge set and somewhat random data. This is a bunch of random integers. I don't remember how many. Sets, however, are a little bit faster than dictionaries. Okay, for real now, enough with dictionaries. Now let's talk about sorting. This code is also from Django 151. And it first creates a list that it wants to return, a return value, and it's going to be sorted. And then it sticks a lot of data into that list. Then it makes it unique by making it a set, as we discussed before, but it makes it a list again because it wants to sort it, and then it sorts it and returns it. Now, of course, the first mistake in this code is to use a list first. That's not a prehistoric pattern. I think it's just a mistake. Probably the list set call was added afterwards when they decided that no, this has to be also unique. But that the first iteration of this code didn't have that, and the person who added it said just, oh, let's make it unique and just make a set, and didn't actually read through the code properly and realized that he could use the set from the start. This is my guess. And sure, updating lists is faster than updating sets, but first creating a long list and then making it a set is not faster than using a set from the beginning. So it's not a performance question here either. But the real point here is this change that I did in the comparison in the code here, namely I changed from sort on a list to sorted. So here we use a set from the beginning, so we don't have to call set to make it unique, and then I just call sorted on it. And this is the modern version, and I'm sure you've all seen sorted. So the question is why you would sort on a list instead, and that's because sorted didn't always exist. It's also Python 2.5. Sorted also takes any iterable, so the code is more robust. In this case, we're sure it's a list or in fact a set. But you can, with sorted, pass in to whatever is going to sort things. You can pass in, for example, a generator, and it will work, and that makes it possible for you to make faster code. So you should use sorted and not sort in general. Calling sort on an existing list is a little bit faster than calling sorted on the list, but because that ends up creating a new list, but it's a very small difference. The next old sorting pattern is all about speed, and you will not find it in Django 1.5 because Django 1.5 supports Python 3, and this pattern doesn't work in Python 3 anymore. But when you're dealing with Python 2 code, it's still quite common to see this pattern. So this example is from Plone. It's even from an old version of Plone because they fixed it now. So this is Plone 4.0, so it's several years old. That's the newest code I could find in a major framework. And this first takes a copy of the list, and that's a good indication that it's old because it's going to use sort on it later, and sorts in place, and that means you modify the original list. So quite often when you use sort, you don't want to do that, so you make a copy of the list. And then it calls sorted on it, but that's not the point of this pattern. This pattern is that the point here is that it's using a comparison function. And what's the problem with comparison functions, you say? Well, this comparison function, it compares pairs of things. So there's always two objects being compared. And the longer the list is, the more compares, the more combinations of objects you have. So here is an average made by Jared Hardy in Python magazine years ago of how many calls you get to the comparison function per item, depending on how long the list is. So for a list with 40,000 objects, you'll call the comparison function 342,000 times. Means that you call the modified method on this object 685,000 times. The modern version is, of course, to instead use a key function. The key function just needs to return something that is sortable. So a list or a number or a tuple, anything that is sortable. A tuple of sortable things, it has to be then. It becomes a much easier and simpler method, as you say. And how many calls do you get per object? You get one, always. It's exactly one. And that means that for a list with 40,000 objects, we get 1/17 the amount of calls to modified. It's going to make sorting this list basically 10 times faster. So this is one of the few patterns where you encounter it. I will tell you to think about maybe fixing it, actually, in the code. Because this is something that actually makes a huge difference. And the comparison function, which was the only way you could do this up to Python 2.4, I don't remember, something like that, was essentially just a bad idea. Next pattern is this, and I would expect most of you to actually have seen this. This is very common. And this is also, this example is from Django 1.5. And it looks like it's a logic expression, but in fact it's not a logical expression. It's a sneaky conditional. What happens as a result of this is that if include blank is true, then first choice gets set to blank choice. If include blank is false, then first choice gets set to an empty list. That's the intention of this. But what happens if blank choice also evaluates to something false? If it's an empty string or an empty dictionary or none? Well, then first choice gets set to the empty list. In this case, this example from Django, that's not a problem because putting in a blank choice that is blank or a value to false doesn't make any sense. So it won't actually create any bugs, but it will make it very hard for you to debug if you pass in a blank choice. Because you can do that and Django will continue to work happily and it kind of looks like it works. But that's just actually an error in you calling this method that gets hidden by this expression. It will behave like include blank is false. So if you set then include blank to true and you realize that first choice is an empty list, then you'll get very confused and wonder what's going on and you have to start debugging this. There is a new, in quotation marks, that's in Python 2.5, syntax for this, and this is conditional expression. So you say instead blank choice if include blank else square brackets. This does not have this problem. If you say blank choice, if you set that to none or an empty list or an empty string, first choice will be set to an empty list or an empty string if include blank is true. But when you encounter this, and this is very common, this something and something else or the false return as a very common one. So I'm sure you have encountered it already, and if not, that's how it works and what it should be. Now we're going to discuss something slightly more unusual here, and this was suggested to me as a pattern I should bring up because it's outdated, they said. And this is a very simple thing. You calculate a constant outside of the loop. Calculating the constant outside of the loop should reasonably speed up the loop, right? Because you don't have to calculate the same constant over and over again. So let's see what happens there. Well, turns out that in fact in Python 2.5, Python will find this constant, realize it's a constant, and keep it in memory and will not recalculate it for every loop. So it's an outdated pattern. You can put constants inside of the loop, constant calculations inside of the loop, right? Well, it turns out not if you have a division. If you have a division in it, Python will not optimize that away in Python 2. But it will in Python 3, and PyPy will also optimize it away. Of course, this example is essentially a pretty stupid example because 5 times 3.5 is 17.5, so you can just put in the result. And even worse, you can just make this instead. So this is a really bad example. Let's take an example that is a little bit more sensible. In this case, the constant is only kind of semi-constant. It's constant through the loop. It doesn't change in the loop, but it depends on some other variable in the software. And I don't just add it to result, I multiply it with something that I loop over. So this is a more realistic example. And how does it look then? Well, then it's only PyPy that can succeed in optimizing this. So you think then, okay, I can put these kind of semi-constant calculations inside the loop if I run on PyPy. Well, not if you have a power. Then it suddenly becomes 33 times slower to do it inside the loop. Because I don't know, and they can fix this in 2.0. I haven't tried with 2.0. I had 1.9 installed, so I did that. But that's the point, is that it can, you get all these edge cases. You'll have this really fast and nice loop, and then you go, oh wait, actually I'll change it around a bit and change it to something else, and suddenly it gets really, really slow. So it turns out that this prehistoric pattern that was suggested to me that I should include from people on Twitter and Google Plus when I asked, because I only had a couple of few patterns when I started this, and I said that will make a good lightning talk. And people said, no, you should make it real talk. So I asked for patterns, and I got a lot of patterns back as suggestions, and this is one. And it turns out several people think that indeed you can today in CPython put constants inside of the loop. It shouldn't be a problem. And it turns out it is. This pattern is not prehistoric at all. You should calculate the constants outside of the loop, which is, of course, the intuitive way of doing it. And this is the pattern that was the catalyst for this talk. This is what started the whole thing. When I said I should do a lightning talk about things that are misunderstandings depending on old things. And here I was wrong, because this is Django 1.5 again, and the code, see if you see it, I don't know. It takes two variables, bytes and self leftover, puts it into a list, and then it does join on that list. And there are bytes, but it doesn't matter. Bytes or strings, it's the same thing on Python 2.7, and bytes are a little bit faster on Python 3. And several people have said that this is because join is faster, right? Using addition to concatenate strings is slow. This is something that a lot of people know in the Python world. But the thing is that since Python 2.5, there are optimizations in string concatenation, so now it's fast. But PyPy doesn't have optimizations unless you use a compile time parameter, says the PyPy people. So then it's time to look at the benchmarks. And then it turns out that in fact, adding two strings instead of joining them is always faster except on PyPy. These benchmarks have been a big problem. It's been very hard to get something sensible, simple, and that measures concatenation that PyPy doesn't completely optimize away and is 50, 60 times faster than everything else. So yeah, but this is the best I can do. It adds strings between 1 and 999 characters long, and there's overhead in these tests, but I'm fairly sure that that overhead is not enough to make a significant difference. And you can see that using addition is faster even on Python 2.4 before those so-called optimizations. And in fact, the optimizations doesn't seem to make anything better. Python 2.7 is slightly slower than Python 2.4. So you wonder then, where does this claim come from that join is faster than using addition for strings? I think it's a big misunderstanding. And I think the misunderstanding comes from this. This is very slow, right? You have a list that contains a bunch of strings, and you loop over that list and concatenate and add on each bit of string every time, and then you return the result. That's slow, but this is fast. You take the list and you join it. And if we look at the statistics for that, using join here is about twice as fast, again, except on PyPy, where it doesn't really make any difference. There's probably some magic. On Jython, there's an enormous difference. So Jython's string concatenation using add is really slow. But, as you saw earlier, as long as it's just 2 strings you're adding, using plus is faster on Jython as well. The reason for this is quite simple. The first time you start with an empty string, and the first time in the loop you take this empty string and you copy that empty string, and that's fast, and then you copy the first item in the loop to the end of that empty string, and you stick that into the result. And in the next loop you take the first item that you had again, and then you copy that, and then you take the second item and copy that. In the next loop, you have the first and second item, and you copy that, and you take the third item and add that on, and so on. So if you have 10,000 items, the first item in that list gets copied in memory 10,000 times. That's going to be very, very slow. In this example, here, each item in this list is copied once, exactly. So that's why concatenation is slow. It's slow if you repeatedly do it in a loop. And that's why join is fast. Join is the way to add lists. That does not mean that you should create a list and join it, because this also copies each of the strings only once. So does this, of course. The join only copies the strings once, but now, before you copy them, you have to create a list. And that also takes time. It's not a big difference, but it's a little bit of an additional difference. The question then is when to use what. If adding strings are fast when you're adding 2 strings, and joining strings are fast if you have loads of strings, where is the breakpoint? And the answer is that it depends. It depends on how long your strings are. It depends on how many strings you have. And with typical cases, it seems that join is faster for CPython at around 4 to 5 strings. Yeah. So at around 4 to 5 strings, that's typical for CPython, unless you have a really crazy length of strings, very short or very, very long strings. With PyPy, up to 10 strings are about as fast to use addition for as to use join. And then I stopped because they were getting silly, because who's actually sitting and was like, well, string 1 plus string 5 plus string, like this in a long row, and you have several rows of strings that you're concatenating. So it started to look, the code is starting to look silly, so I stopped. And there we reach the closing concatenation conclusions. I like alliteration, can you tell? The closing concatenation conclusion is that you should do what feels natural. If the easiest way to concatenate a bunch of strings is by using plus, then use plus, right? If the strings you have are in a list or they're generated in a loop, then you use join. And the same goes for calculating constants outside of the loop. It feels like it should be faster, and quite often it is. Sometimes, though, your Python implementation will optimize it away, but quite often it will not. So you calculate the constants outside of the loop because that feels right. And this is, in my opinion, why Python is such a fantastic language, because what intuitively feels right to do tends to be, in fact, the right thing to do. And on that bombshell, I say thank you for listening.